So on the latency side of things, this is actually a pretty clever method that's used for calculating this that breaks us down again into those three tranches of client delay, server delay, and application delay. We'll see those get calculated in an interesting order. But really, this starts with some sort of device that's measuring this traffic. Again, for the Plixer platform, this is a Flow Pro, but we can collect the data just as easily from any device that's able to run these metrics and export it over IPFIX. But the conversation really begins when a client sends the initial SYN packet to a server. The SYN packet goes to initiate the TCP handshake. It passes through our observation point, and at that point in time, a timer starts that is associated to the flow cache for this specific conversation. When the SYNAC comes back from the server, we finally have kind of our second piece of information passing through our observation domain, again, the probe or Cisco AVC device, whatever it may be. And now we actually have a measure for the delay moving between our observation point and the server. We saw the SYN go through, started a timer, a SYNAC bounced back off the server, and we can actually now set in stone that that is how long from our observation point it takes network traffic, at least of this class, to move to the server and then back to the observation point. So we have our first measurement at that point, our server network delay. Ultimately, the client will act back, acknowledging that the synchronization acknowledgement came back from the server, and we have a second bounce now that can be used to enumerate our client network delay. So we now, in the first step, SYN-ACK, we get our server side network delay, ACK to, or SYN-ACK through, and then the ACK from the client, and we have our client network delay. So at this point, for any of those instances when we were looking at kind of the retail topology, we immediately have an idea from the point we're observing what is the network latency on the client side, what is the network latency on the server side. Two metrics that we can use to either pinpoint kind of what side of an interface our slowdown is occurring or drops or whatever it may be. And then ultimately giving us a place to start framing where in the network a slowdown or performance issue might lie. Finally, after that handshake's completed, the application will send an initial app data request or whatever it's actually going to use that TCP conversation for, and then we'll get a data response from the server itself. And ultimately, what that enables us to do is we now have a composite in that measure. We know what the server side network delay is from our previous calculation in the handshake. And now there'll be some additional latency that's observed there, and that can be attributed to the application itself. Again, we know what the network delay should be between our observation point and the server. So really anything over that is going to be time that was spent in the application before it could package up the response, throw it on the socket, and fire it back over to us. So in composite, we have our three metrics here. At first, calculated our server network delay, then the client network delay, and then ultimately the composite of the server network delay and application delay. So the final part of the process for the calculation it's happening against the flow cache, it will subtract out that network delay from the application delay or the overall delta that was observed during the app request and app response, and leave us with just a pure application delay. So we now have those three metrics. And again, this is very powerful, specifically when kind of going back and forth with an application team where it's not speculative. It's not, it seems as if we can actually show in hard data, this is the delay between our observation point and the client. This is our delay between the observation point and the server. And this is ultimately how much time was spent waiting on the application to respond. And again, subtracting that server network delay out is really the powerful part because that's what completely removes all of our network state from the actual time spent dwelling in the application. So again, if the application's high, we can point to the app team. If server or client network delay is high, then we already know it's something that we can solve from the NOC perspective. Secondly, thinking about RTP and jitter, RTP is stateless. It's effectively the client or the server spraying data at a listener. And ultimately in RTP conversations, those applications are working around a jitter buffer. So a jitter buffer is meant to absorb some variance in the inter-arrival time of packets. It's typically like 30 milliseconds. So if you think about humans, we are interfacing with the world with a delay of like 100 plus milliseconds, between 100 and 200 milliseconds. So ultimately, anything down at like 30 milliseconds is going to be far below our ability to perceive a difference. So when a packet, has some variability between how long has, how much time has passed since the previous RTP packet arrived and the next one's coming, we have that 30 millisecond jitter buffer in the application to absorb those things. What's really important is understanding with our applications how sensitive that buffer is going to be, and then ultimately getting these measures off the network to figure out how much variance is in that time delay or time delta between packets, and comparing it against the jitter buffer to see, is this inter-arrival variance high enough to result in a observable performance impact in the application, getting to the point where voice starts to break down or video starts to get kind of choppy and weird. So you can start to see if there's one kind of bend in one of these lines, we get a much bigger delta between packets. You may run into a case where the time between packets is longer than that jitter buffer, and that's when the actual performance impact will start to be felt by whoever's using that real-time application. Whether it's security cameras that are just recording everything. Typically, security cameras are at much lower frame rate. You don't really want to drop a packet because that's, the lower the frame rate, the bigger the deltas that were happening per frame. If you lose any of that data, it fails to make the jitter buffer in time in order to be recorded. You end up with basically half the frame rate for that period of time and lots of information loss in between. Similarly, with voice calls, you start to drop or start to get large delays in the voice data that's coming. It doesn't necessarily have to be dropped altogether, but if it gets there too late for the application to use it, then real time's already passed and it's really not helping anyone to play some vowel sounds that I made a second and a half ago now, since the context of real time and real time protocol is actually what's important.